arc length today. It's much like finding volume or area. It's another formula. You just have to be able to apply that formula. Fortunately, a lot of times you don't have to even calculate the answer. They just ask you for the setup, right? So that's kind of nice. If I give you some function on an interval from A to B, function has to be continuous, obviously. Is it very easy to find that arc length, the length of this line from here to here? Okay. You can do a straight line pretty easy with the distance formula, right? But now we're moving on to curved lines. Okay. So if we were to approximate this, just like you approximate area with Riemann sums, right? We can partition this into different sized chunks. How might I approximate that length of that line using those partitions? What? Yeah, so we could approximate with straight lines between those, in those partitions, right? You'd be pretty close. Just depends on how steep the curve is and stuff. Okay.
Couldn't you also, so like an interval calculates the area between the curve and x-axis. So couldn't you just use the interval to find the area and then use the area calculation backwards to find it? Or is that not one?
That's a good question. If, so you're thinking find the area, go backwards to find the length of this.
But as I think about it more, you come close to the diagrams.
The problem is you don't, yeah, you're working with straight lines again. You could approximate it. Like if you found the area and you knew the average value of the function, you could find the average value gives the height of that rectangle.
Right.
You could find the approximate straight line length of the function, of that arc. Yes. Okay. But it would not be, it would be much less accurate than the distance formula. What if these are our partitions, I set this partition size to 1. Could I use the Pythagorean theorem so I can calculate the length of that hypotenuse with the Pythagorean theorem, right? The question is, what might the height of that triangle be? How could I calculate it? Without knowing the hypotenuse. Trig?
Yeah.
Is that what you said? If you know the angle? Do you know the angle?
I don't.
Okay. Can you calculate it without the hypotenuse length or the leg length? No, we can't. Okay. How steep is that line? Huh? Who knows? Can you calculate it? Right? Can you calculate the slope of that line? And would the slope help us to figure out how much rise there is over the run? Slope is rise over run, correct? We know the run is 1. So this is just the rise of the slope. How do we calculate slope in calculus? It just so happens that that is the derivative. This is 1, right? So what is the length of the hypotenuse? Pythagorean Theorem, 1 squared plus f prime of x squared, right? So h is the square root of 1 plus f prime of x squared. Right. There's another way to approximate that. Well, it's the distance formula basically, because that's built off the Pythagorean theorem, you know. Okay, so here's what's really neat is that the formula for arc length is actually built off of that concept. So the arc length formula just happens to be that right there. All right. So it comes directly from those partition sizes, right? So just a big idea for you where that comes from. It's not formal, but where? S? That's an S.
So that formula implies that you only use a 1 for that?
Yeah, we're just making that partition size a set value. Makes it easier, right?
Mm-hmm.
Yeah.
But will that ever change in your formula? Or is that
Nope,
always
formula's always the same, thankfully. Yeah. So let's look at a couple of these and calculate some arc lengths. That would be good. Let's see. Find the arc length. S of x.
But how accurate can that approximation be? I mean, because like with regular integrals, it's using.
This is not an approximation. When you include the integral, it's an exact.
Right, because like integral we use like an infinite number of
Yeah.
Riemann sum.
Yeah, so I kind of sheltered you from going from approximating to exact, right?
Right.
This will involve a limit. As you were saying, the partition size goes to 0 or the number of partitions goes to infinity. That's what an integral is, right? So, yeah, there's a little bit of theoretical calculus between the two of these, but you get the idea of where it comes from. It's how people think through this kind of stuff to develop new formulas. Okay, so again, I always recommend if you're memorizing these formulas, because this is yeah, we will. When you're memorizing new formulas, you always want to just write them down every time you have a problem with it, right? Because it just repetition, repetition, repetition. Okay, so we need f prime of x, correct? All right, what is f prime of x? Is that right? Yeah. Do you want to square that now or later? Because we have to square f of x. Well, it saves you a little bit of writing if you do it now. So sometimes the problem will say, write but do not evaluate an integral for the arc length of s. Arc length s of f of x, right? So your answer would be that right there, correct? Oop, too far. Okay, that would be an answer to that question. Write but do not evaluate an integral. Okay, we jump to the ceiling for that because sometimes those are pretty nasty. But sometimes not, so I would recommend doing it separately. All right, sound's back now. Let's do this. And you can even add your 1 in now if you want. 1/16 x to the 4th plus 1/2 plus x to the negative 4th. Okay. Any ideas on how to solve that by hand? Because it can be done. How do you get rid of roots? Squares, right? Squares and square roots eliminate each other. So is this a perfect square? It's the question you kind of want to address there. Yes is the answer. 1/4 x squared plus x to the negative 2 squared. Okay. Probably the most difficult thing to see in a lot of these problems is how to eliminate the root if it's doable by hand. Good? So we can eliminate the root, and we just have a basic integral, a polynomial integral now.
So we solved for the squared equation of 1/4 x squared minus x minus 2, or x to the power of 2. Why would you do that if you just want to end up with the same square?
They are different. Negative. So you have to put that 1 in there.
Okay.
And then see if that resulting polynomial is factorable, right? Because we can't just root 1 and root that. it causes, it's an algebra atrocity and a puppy dog would die. We don't want that to happen. Yeah. Okay. Do I need to finish that? Or are you good? Okay, no answer. I will just write the answer down. If you do the math, you get 17 over 6. Okay, good? You guys are off the wall. Tired, huh? Calculate the arc length of cosine x over, no, let's make that, flip the book, sine x. 0 pi.
What's the application of this?
Ooh, do we need to go there? Any computer modeling that's done.
Or did you use it?
Okay, is there anything in airplanes that has a straight line on it? The fuselage. Is the wing a straight line? Is the engine housing a straight line?
Not really.
Okay, so how do you figure out how much sheet metal you need? You model it with a polynomial, do the calculus. Computer does it all for you, right, nowadays, but used to not have that. So, yeah, lots of applications for airplane. Surface area tomorrow, same deal. Like volumes of rotation. So if you figure out arc length, you can do surface area, you can do those volumes of rotation, you can do how much thrust the airplane is. You know, if you do a velocity equation with vectors, you can do thrust from volumes of revolution, all sorts of stuff. So, okay. All right, what's our derivative here? Cosine x, right? So, again. Write out the formula, just to memorize it. So we have 0 to pi, 1 plus cosine x squared. Right? Is there any way for us to do that by hand? Like, can I get rid of the root? Or can I integrate cosine squared? No, none of that's friendly integrals. All right, so this is at the point where you would say, I can't do that by hand, I need to use a calculator. Okay, this would be one of those questions they say, write the integral but do not evaluate it. Good example. Or you use your calculator if it's calculator friendly. Right, so throw that in a calculator, making sure you're in radians mode because my pre-calculus class is using them in degree mode. Okay. Hoping that David's right, all right? The book has 3.820 as an approximation, so that's about it. Do you have any questions? Okay. Since this is in Chapter 8, there are a couple of integration techniques you haven't learned yet, and I think I found them and took them out of the assignment, but if you see something that you don't know how to do, just bring it tomorrow, or Friday. We won't grade this till Friday. And I guess you could ask tomorrow too. Make sure those AP problems are doable. Oops. Yeah. Okay. Shout if you have any issues.